welcome with me Mr. Everett Anderson, VP Electrochemical Technology from Proton OnSite.
Thank you. So I'm going to give an update today on our PEM technology, electrolyzer developments, primarily focused on megawatt scale electrolysis, which is, I believe, of most interest to this group. The outline of my talk today, just a brief introduction about Proton for those that don't know us, and then talk a little bit about generally energy storage needs and the motivation that we see for developing megawatt scale electrolysis. Talk a bit about the characteristics and capabilities of the PEM electrolyzer, and then move into discussion of our product development efforts and kind of where we stand today, specifically focused around this next generation cell stack that we're developing. So Proton has been around since 1996. We've basically look at ourselves as the leader in PEM electrolysis technology. We've got a well-established commercial business with a customer base now of well over 2,000 customers around the world. We're in 80 different countries. We've seen significant growth in our business over the last 3 years, 50% growth. A lot of that's driven by the commercial business, but we're also, again, beginning to see the beginnings of real businesses on the energy side as well. And because of that, we're continuing to scale up our manufacturing capability. We are a manufacturer of PEM. We make our own stacks, our own systems, all the way down to the membrane electrode assembly, and then we package those systems where needed for customers with ancillaries like compression and storage. Our industrial markets are on the left, where you see primarily power plants for electric generator cooling is our main interest. We also serve the semiconductor industry and the metals heat treatment industry. And then you see the energy markets on the right, the emerging markets in transportation, energy storage, and backup power. So our motivation as we look at megawatt electrolysis is really threefold. One, in basically large-scale energy storage, with the motivation of tens of gigawatts of wind and solar energy capture needs coming. A subset of that is the power to gas concept, taking this excess renewable energy and injecting it into the natural gas grid. We also see a parallel path in biogas upgrading as, again, another very interesting and promising market for renewable hydrogen. And then lastly, the transportation market, where there are infrastructure plans growing both in the US, where Proton is based, but also predominantly in Europe and Asia as well. Each of these three market opportunities is a multi-billion-dollar opportunity for electrolysis, and each of these needs multi-megawatt scale electrolysis. So that's our base motivation. Again, just some background slides. There are many power to gas demonstration projects already underway, primarily in Europe. A lot of these have been served by alkaline technology because of the existing scale of that technology, but the trend is towards looking at PEM for these applications as well. The whole idea of hydrogen as an energy carrier is kind of illustrated here. I stole this from Christopher Hebling at Fraunhofer, where you kind of see the marrying of the electricity grid, the natural gas grid. You've got the basically heating, thermal side of it on the top, and then mobility on the bottom, and basically water electrolysis being at the nexus here, serving these various applications and being able to transfer the energy from one grid to another is a key feature. And then we talk, as again, when we're talking large scale, we're this is again an old slide from Charlie Fries at GM, kind of showing the magnitude of the opportunity for hydrogen and comparing it with basically underground storage, basically battery storage in vehicles, pump storage, and the boxes are representative of basically the ability of hydrogen in comparison to these smaller boxes you see in the very low left-hand corner there. So really that's where hydrogen could potentially serve this market, is in seasonal energy storage, very large scale, and certainly that's the exciting opportunity for us as we move forward. We're certainly well experienced in the transportation side as well. We've done multiple, I think over 30 projects now. Our equipment's in fueling stations around the world. We have a fueling station at our facility in Wallingford that boasts the largest fleet of Toyota fuel cell vehicles in the world at this point. We've got a dozen fuel cell vehicles based there. And that station's been running for the last 3 years, with getting a lot of experience in managing a station, but also understanding the delivery of fuel for that application as well. So the advantages of PEM electrolysis really boil down to safety, efficiency, and then response time and dynamic range. So you kind of see a comparative chart here that looks at PEM efficiency as comparison to some alkaline technology that we pulled from the literature. And the two curves for the PEM is basically where we are today, and then where we see the technology moving as we kind of go forward. And it goes along the lines of a presentation by Jürgen Mergel that presented earlier, where you see the advantage of pushing the technology out, both in terms of increasing the efficiency, but also being able to run at higher current densities in order to minimize the capital cost. We believe we've got the most proven and reliable technology out there in the market today. We've consistently shown basically lifetimes. This is some, a bit of a legacy kind of chart now that we've shown, 50, 60,000 hours of our own testing internally, and we've got multiple customers, if you will, that can testify to the longevity of the systems that are actually in real-world industrial applications that have been in the field for 7, 8, 10 years now. It also shows basically some advancements with our own commercial technology that's out there. Basically, the top curve was Legacy 2003 that showed a slow but still positive decay rate, aging of the cell stack. The bottom line is a newer version, actually not that new, started in 2005, where we've basically essentially designed out that voltage decay through improvements in materials, improvements in process. And then we feel our experience with the industrial systems that we have today really is a solid foundation for moving to this megawatt scale product. We've got a progress from small laboratory systems to medium-size multi-stack systems, and we've kind of proven this multi-stack technology. We're using that same architectural approach as we look to the megawatt scale product. So in terms of the product overview, basically we're designing a modular approach. It will be a 2 megawatt base product. We'll also have a 1 megawatt version available. This will be commercially available probably mid next year, and we're actually beginning to take orders for these now currently. It's a multi-stack architecture. You can see at our booth 250 kilowatt stack design that we're working on. So we'll use 4 of those per megawatt. And it's a larger active area platform. We're going up 2 to 3 times larger than where we're operating commercially today. We'll also have containerized versions optional, basically ancillaries tailored to the customer's needs. This just kind of shows why we believe scaling up technology further will be able to meet the price targets that the market is looking for. So this is just a kind of snapshot of 3 sizes of electrolyzers that we produce today, from a 1 normal meter that dates back to back in 2000 when it was first commercially introduced, to our latest commercial product today, which is the C series, which is a 65 kilogram a day system. And what you see there is, as we've increased in output, you don't scale linearly in capital costs. So I've normalized the capital cost and the bottom line there to the original S series system, which was a 7 kilowatt system. If you look at the C series today, it takes 175 kilowatt input, but on a dollars per kilowatt capital cost basis, it's less than 70% less than the 1 normal. We see that same cost trajectory going as we go to the megawatt scale, and because of that, we think we can meet the market price targets. Just another discussion of cost curve. So this is a comparison I put together. I plotted some of the basically the prices of PEM electrolysis on a specific cost basis. So this is per $1,000 US per normal cubic meter per hour. So a kind of normalized capital cost, and then production capacity on the bottom line. And what you see is exactly as I said before, as you move up in scale with PEM electrolysis, you start to approach other generation technologies in terms of price. So this compares some data that I pulled from a hydrogen implementing agreement task where it looked at small scale reformer technology, large scale reformer technology, and you see that the curve is not too different as you go to these larger and larger systems. So this is just a snapshot. It's a busy slide of our technology roadmap on the cell stack. We've got a lot of history on the left-hand side with small 2 meter size units that we produce today for our H series system. We've done a lot of work looking at alternatives at this 2 meter platform, bipolar plate technology, various cost reduced architectures, proven that out at small scale, and then use that basis to apply to these larger scale active area systems. So that's what we're doing right now. We've basically moved to a cost reduced large active area platform that we're baselining for our megawatt product. We've got experience with the smaller round designs and scaling up to the C series stack today is 65 cells. So we look to basically the full scale 250 kilowatt stack platform will be a 100 cell stack, and we think that all the expertise over the years at these smaller systems and smaller scale feed into being successful at this platform. I will say we're choosing the stack. It's not an arbitrary choice. We're looking at the capabilities of our supply base, the capabilities of our manufacturing technology, and we feel that this is the right size active area for today in order to minimize risk and maximize the advantage in the market. This is just some testing that we've done. So we've got tens of thousands of hours of testing at this larger active area scale now. Now we're in the process of basically scaling the technology up to its full 100 cell active area size. This involves no easy task when you start having to put in the infrastructure in order to test at hundreds of kilowatts to megawatt type level. So certainly there's time involved in getting there. The upper right just kind of shows a difference in scale between our smaller active area test cells that we originally kind of proved the concepts out, and then the 7 times scale up to this larger active area that we're using now. We've done a lot of work looking at Paretoing the costs and attacking basically the highest cost elements to get to this larger active area stack platform. So this just shows the 3 highest cost elements being the flow fields and separator plates within the stack, based on the fact that they're based on semi-precious metal. They're typically noble metal plated. You have the MEA, the membrane electrode assembly, as the second element, and then obviously you've got a labor component as well. So, and then you can kind of see how this breaks down in the context of the system, where the stacks are the predominant cost item within the overall system, but power electronics and other things in the balance of plant are not insignificant cost as well. So this is the work that we did to basically come up with this new design, and really we attacked reducing the cost of the flow fields and separator plates primarily, as well as taking labor out, and a small amount of reduction in the cost of the MEA. And what we realized with this larger active area platform is a 40% cost reduction. That really is a key enabling technology for the megawatt product. So this is just a picture of it here, a Gen 1, Gen 2 version. So the Gen 1 on the left was kind of an initial prototype, slightly smaller active area, had about a 600 square centimeter active area or so. We did a lot of testing and durability on that stack, and then basically turned the design to what you see on the right. So we actually got 15% more active area in that stack. We were able to shrink the overall footprint, again, taking material out to reduce cost. And that's the item that we have today that's at 40% lower cost. I want to talk just a little bit, switching gears, to talk about the kind of the operating conditions or functionality of electrolysis. This is kind of a faded chart, but one of the things that's been talked about is overcapacity and the drivers for overcapacity with PEM electrolysis. And the idea here is that you can arbitrage when the electricity cost is low in order to basically move along this current density line in order to maximize the amount of hydrogen that's being produced from your electrolyzer as a function of that electricity cost. So having the ability to run overloaded, to run it beyond its rated capacity, is a key feature that we see potentially in the marketplace, and it's a key feature that PEM electrolysis has that alkaline electrolysis does not have from a functionality perspective. So again, this is a pretty busy slide, but we've kind of started moving in that direction, doing some initial testing at our large active area size unit. So we're looking at basically what you see here is the blue line is the current density. So that's on the right-hand side, or stack current, I guess is what it's in here. And so we've been able to basically not only run at its rated output, which is basically along the lines here, we've been able to run at an overload condition. This is about probably 175% overload, so up above 1,800 amps of current through the cell. We've also been able to show the dynamic range by cycling it down to very low levels and cycling back up. And the key feature that you see here is I've plotted a combustible gas sensor in the oxygen output. And what you see is very little impact of cycling the stack against the mixture of hydrogen and the oxygen stream. And that's the real key issue here. Because typically if you run at a low rating, the diffusion of hydrogen back to the oxygen side is a fixed amount based on the pressure differential and based on the active area of the cell. So you have to be able to manage that, otherwise you're going to run into an unsafe condition. That's one of the areas of expertise that Proton has developed over the years and years of developing these systems, and is being able to manage that combustible gas. And one of the reasons why we run at high differential pressure today is an advantage. And then, so we've got all of this variable load, we've got this overcapacity. Why are we doing this? Well, we're matching up with what potentially could be an advantage in the marketplace, and that is not only providing large-scale energy storage, but also providing some type of grid services to the utility for frequency regulation or voltage regulation. So you kind of see here in the US, 3 different ISOs and how they manage their grid through, kind of managing the signals. And of course, nobody does it the same way in the United States. They all have their own kind of signal processing. So you can have California, which does a nice step wave. You have New York or New England, which kind of is very, kind of second by second, and then something in between with the PGM ISO. So these are the kind of data input that we need from the marketplace to understand what we have to design in terms of feature set into electrolyzer. The good news is that from all the testing that we've done, we feel that the electrolyzer has the response time similar to a battery in terms of these short kind of regulation markets, but it also then has the advantages of large-scale energy storage as well that these batteries don't have. So this just kind of shows a couple of slides looking at response time. So we've been able to, with our work with our friends at the National Renewable Energy Lab in Colorado, demonstrate again the sub 100 millisecond response time that an electrolyzer PEM electrolyzer can show. They've also done some durability testing for us. So again, looking at a variable load input and looking at the impact on aging of the stack. And then next slide, we've also done some initial work they've done for us in looking at this frequency regulation application. So by triggering at 0.5 hertz, they've even gone down to 0.1 hertz trigger in order to show that bringing the electrolyzer on load to balance that frequency regulation is certainly an application that that it can handle. Certainly we're not standing still. We continue to look at further cost reductions, both in catalyst, in membrane material. We've got partnerships with national laboratories and universities and private companies trying to leverage all the great learnings on the PEM fuel cell side and apply that where needed and where possible to the electrolyzer. So, and we've seen a lot of good fits with some of the nanostructured catalyst developments, both in thin film technology and core shell technology that has applications to PEM electrolysis. Some of the thinner membrane materials with advanced materials are also showing promise, whether that be in some type of reinforcement at thin size or whether it be a non-reinforced hydrocarbon-based materials. And so again, I think we're continuing to attack those high-cost areas, especially since we've done, I think, the job that we needed to do kind of in the flow field and the cell design. Now we're turning our attention to the membrane electrode assembly as the next high-cost element. So the future needs I see for megawatt scale electrolysis, really the cost reduction areas, we've got a great technology roadmap. We understand what we need to do. We believe we've got 50% of these things ongoing and achievable in terms of a 50% decrease in cost. And there are certainly additional opportunities in looking at alternative materials. It's very interesting to hear the ULIG talk and looking at stainless steels as a potential application in here, again, to further reduce cost. And then certainly taking advantage of automation and better manufacturing techniques as the volumes go up will be a key important element as well. So in summary, we see energy storage as a critical need in these three market areas that I talked about, and I think it's a huge opportunity for PEM electrolysis, and we're very excited. We will continue, as I said, executing on this megawatt class product with market entry in 2015, and we'll also take advantage, where we can, of these complementary markets in biogas and transportation. We plan to contribute by working in demonstration projects, both U.S. and here in Europe, and we think in doing so, we'll maintain our leadership position in this technology area. Thank you.
Thank you very much for this presentation here. Are here any questions right in the audience? Yes.
Yung Yang from Austin Power Engineering. So what's the market price target, do you think?
Well, we talked, that was a topic of discussion last year. If you remember, I was part of a panel that there was some consensus around $1,000 a kilowatt, 700 euro a kilowatt as a target price, capital cost price. We believe with the cost modeling that we've done that is certainly achievable without, I would say, without any type of miracle technology development. It's really just engineering scale up. Certainly, you know, you're not going to be able to make product number one at those prices, but we feel with some reasonable volume we can get to that target. Whether that's enough, you know, for all of these markets, you know, that remains to be seen. Certainly, there's an efficiency component that goes along with that, and those are directly coupled in terms of sacrificing one for the other. So it's certainly not an easy challenge, but we think based on what we know, it's certainly a doable.
Okay, thank you. Is there another one? So, not yet. So, if there are coming any question or problems further in your mind, I think you will welcome everybody at your booth.
Absolutely.
Yeah, it's C70. It's quite close here, just this direction. So, it's your applause again. Thank you for being here.
Thank you
for
very much.
for this topic and interesting presentation.